Okay, welcome everyone. It's my pleasure to introduce Matthew de Courcy-Ireland, who will talk about six-dimensional sphere packing and linear programming.
Thanks very much for the introduction and the invitation, and to all of you for your interest in six-dimensional sphere packing and linear programming. Is the full screen working as it's supposed to?
It looks great.
Okay, great. This is joint work with Maria Dostert and Marina Piasovska. Here's the plan. I'll say a bit in general about the sphere packing problem and the method of linear programming, which bounds from above how well you can solve that problem. Our main result is one step removed from that. It's a bound on the bound itself. So it doesn't say anything about packing per se. It says that the linear programming bound is strictly higher than the density of any packing in dimension 6. So even though the lattices that seem to achieve the optimal density in dimension 6 and 8 are closely related, the method that proves what's the best in dimension 8 doesn't work in dimension 6. That's the negative result that we're proving. And to do that, we construct a fake packing that tricks the method. So the method is also an upper bound for more general things, and that's why it doesn't give a sharp bound in all cases. And we do that using modular forms, which is why I'm speaking about this in this seminar. So the big question here is why 1, 2, 8, and 24? This linear programming method seems to solve the problem in those dimensions and no others. Or does it? Are there others? What goes wrong in other dimensions? To a large extent, we still don't really know, but I can tell you for sure 6 is not on this list of perfect outcomes. So that's the plan. And it's kind of a long story if you start at the beginning. So I'm going to try to start at the end. This is the input we need from modular forms. There is a modular form G of weight 3 and level 48 using 2 quadratic characters, mod 3 and mod 4. It'll have this transform G tilde, which is the Aitken-Lehner transform, the action changing z to minus 1 over nz. For us, n is 48, but you could do the same thing with other levels. And these both have Fourier expansions. So I write e for the imaginary exponential, e to the 2 pi I. And the expansion of g has 7 as the first non-zero frequency. So it starts with a 1, and then exponential of 7z is the first non-zero term. So there is such a form with all the coefficients an and bn on both sides of the transform greater than or equal to 0. And moreover, you can make this constant term of the transform b0 greater than 0.6168. That's what we need, and that's what we produce. And I've put a bunch of stuff in orange here because those are the key parameters. There's a trade-off here where the constraint is that all these coefficients have to be positive or 0. And subject to that, if you can make b0 larger, that's good. If you could make this 7 larger, that's also good if you can make the expansion start later. But you want to do that with the 48 or the level as low as possible. So that's the trade-off. You can increase the level and have more forms to play with, but the bound will sort of penalize you for that. So that's where the modular forms come in, and I'll try to tell you the story of how you go from sphere packing to this. And moreover, we're able to do this with vanishing on an arithmetic progression. These an coefficients are 0 whenever n is 1 mod 4, which is not really necessary for the method, but I'll try to explain how that sort of helps us as well. So that's the basic modular forms question, optimizing this trade-off subject to keeping positive coefficients on both sides of the transform. If you have another way to do that, it would be relevant for this kind of problem. But the original problem is sphere packing. So when I say sphere packing, I mean equal-sized spheres, which have to be disjoint in space of dimension d. You can think of it in terms of the centers. So the centers have to be a constant distance apart, at least. And the goal is to maximize the amount of space occupied by the packing. So delta D is the supremum of the density you can achieve with any valid packing in dimension D. It's known only in certain dimensions, dimensions 1, 2, 3, 8, and 24. So you can imagine in low dimensions, you can attempt some kind of direct geometric argument. I should say 3 is much, much harder than 1 or 2. Hales solved the sphere packing problem in dimension 3 in a famous Herculean effort. And then 4 and higher becomes sort of inaccessible by direct geometric means. So it's very surprising that suddenly in dimension 8 and 24, we know the answer. And that's because of this method of linear programming. Any questions about the basic problem or the plan? So I'll tell you about the bound. This is the linear programming bound due to Cohn and Elkies from a 2003 paper. At the end, I can put some references in the chat if you want to read more about any of this. They start from a function f in d variables and some radius r. And we suppose that f becomes negative after distance r, while the Fourier transform of f is always positive. If you have any such function, you get a bound for sphere packing in dimension d. You can conclude that all packings in dimension d have density at most f of 0 divided by f hat of 0 times the volume of a ball of radius r over 2, a d-dimensional ball. So the goal is to construct a function f that minimizes this bound subject to the sign conditions on its own values as well as the values of its transform. So this r is sort of related to the size of the spheres you're trying to pack. You're free to rotate or rescale f and get the same bound. So f gives the same bound as any rotation because the constraints are rotation invariant. You can rescale both the variable x as well as the values of f. So you have 2 degrees of scaling freedom, and you can use that to fix 2 out of the 3 parameters, r, f of 0, or f hat of 0. So if you think of r as fixed and f hat of 0 as fixed, then you're just minimizing f of 0, which is a linear functional of f. So you have a linear objective and linear constraints, and that's what makes this a linear programming bound. So there's a whole theory about linear programming, but this is infinite dimensional because f is a function of a continuous variable, which you can think of as just the radial distance. So the goal is to find an f that works. So if you haven't seen this before, the first remark to make is that there are f. The bound definitely gives something. So recall we want f hat to be positive. So one thing you can do is make f hat a square. So in other words, f is a convolution square. So you can always just take f to be the indicator of a ball convolved with itself. And that satisfies all the constraints, and it gives a non-trivial bound for the density. Another thing you can do is take a polynomial in the squared distance times a Gaussian. Finitely many inequalities on that polynomial will guarantee that f satisfies all the constraints. So this is very computer friendly. You could say the degree of the polynomial is 10 or however far you want to go and solve a finite dimensional linear program and see what bound you get. And you can do it in a rigorous way so that you know for sure f satisfies the inequalities. Like it's not just a very small negative number, for example. It's really 0 or greater. You can do all of that rigorously and get rigorous bounds. What's not clear is whether you could improve your bounds by taking a different f. So for instance, you take degree 10 polynomials, you get one bound. What if you took degree 20? How much better does the bound get? It's not so clear. But Cohn and Elkes were able to implement this and get bounds, and they noticed that it seemed to be matching the density of a known configuration in dimension 8 and 24. So there are sharp cases of this bound. So in dimension 1, you can just take the convolution square, and that already gives a sharp bound. The density in dimension 1, I mean, obviously, you can fill up all of a line by disjoint intervals, except at the endpoints. That's not a difficult problem, but it is interesting that an f actually recovers that. In dimension 8 and 24, those were the breakthrough cases where Wiesowska constructed an f that matches the density of the E8 lattice. And shortly after, Cohn, Kumar, Miller, Redchenko, and Wiesowska gave a similar construction for the Leech lattice in dimension 24. Dimension 2 is still open. Numerically, it looks good, but we don't know how to construct f. So that is still open. And I should also say that when the method works, it gives much more than packing. So E8 and the Leech lattice, or even the integer lattice in dimension 1, they're not only optimal for packing, they're also optimal for a whole family of problems. So Cohn, Kumar, Miller, Redchenko, and Wiesowska proved what's called universal optimality for those as well. So these are kind of exotic cases where things work out really well, and it's not clear where they come from or whether there are others. So that was our motivating question. Try to see what goes wrong in dimension 6 or what goes right in dimension 8. Any question about the context?
And what led you to 6?
Well, the truth is that we also tried 3, 4, 5, and 7. And 6 was the first one that worked. But 6 is interesting because in dimensions 3, 4, and 5, it seems you can get the highest density using the Dn family of lattices. But starting in dimension 6, there are these exceptional root systems, E6, E7, E8, that do better. So 6 is interesting from that point of view. It sort of tells you whatever's going right with E8, it's not a feature that is shared with the rest of En. So here's a sketch of a proof of the Cohn-Elkes linear programming bound. I think I'd better skip it in the interest of time, but it is a very short, elegant proof that I'm happy to come back to if you haven't seen it before. What I want to talk about is duality. So in linear programming, every linear program has a dual program, and that's how we get a bound on the bound. So if you have a function f as before, so f becomes negative after radius r, f hat is always positive or possibly 0. There's now a dual thing, mu. Mu will be a measure. We try to integrate this f against the measure mu. So mu has a Dirac delta at the origin, and then some other term. The other term is supported outside the same ball where f changes sign. And then the Fourier transform mu hat has to be at least some constant c times a Dirac delta at 0. So we assume we have such a mu, and then the claim is that it gives a bound on the bound. And that follows just by discarding terms. So f of 0 is at least integrating f against mu, because f is negative after radius r, and that's the same region where mu is supported, except for that spike at 0. So you discard everything except the spike at 0, and that gives you f of 0. But then you have Plancherel. So pairing f with mu is the same as pairing f hat with mu hat. And by similar reasoning, we can discard terms. So mu hat is at least c times a delta at 0. F hat is always positive. So we're getting at least c times f hat of 0 from pairing mu hat with f hat. So we conclude that if there is such a mu, then for any f of 0 is at least c times f hat of 0. So if you recall the bound, it was stated in terms of the ratio f of 0 divided by f hat of 0. And we've just shown that that's at least c. So if there is such a mu, we conclude that the linear programming bound is at least c times the volume of a ball. So here, for simplicity, I assumed it was the same r in both places. But you could always rescale. So if you just started with mu and it had some radius, the same argument would apply for all f, because you could rescale space to make f have the same radius as mu. So there's no loss there. So this is kind of a well-established theory in linear programming. There's duality, where you can switch the variables and the constraints and change a minimization problem over f into a maximization problem over mu. So it's sort of a classical topic, but in this context with the infinite dimensional program for packing, it goes back to Kohn around the same time as the Kohn-Elkies bound. And Torquato and Stillinger also had a version of this where they were interested in producing mu in high dimensions that behave much, much better than any actual packings we know how to produce. So this is the strategy we're going to use. That modular form at the beginning is just used to write down a single example of mu. And when we calculate everything, the value of c is supposed to be good enough to prove that the LP bound is not sharp. So if you look again at the proof, we discarded terms. So we integrated f against mu, or f hat against mu hat, and we threw away everything except the origin. To have equality, what you throw away should be 0. So except for the origin, f should vanish on the support of mu, and f hat should vanish on the support of mu hat. So what you should imagine is that mu is sort of a pure point measure with a bunch of Dirac delta spikes at certain places, which are the zeros of f. And likewise, on the Fourier side, f hat vanishes on the support of mu hat. And we also have these sign constraints where f changes sign at some point, and f hat is always positive. So this is what we're aiming for. And I can show you how well we do. So recall that f is computer friendly. You can certainly compute examples of f that seem to be converging to the best f. You just don't know how fast it's converging or when to stop. So here we took a Julia package written by Delatte and Leyenhorst, which computes a polynomial times a Gaussian and verifies that it satisfies the constraints and tries to optimize the bound. So in green, we have some polynomial of degree 24 in this case. And in blue, this is the mu that we construct. So it's a bunch of deltas at certain squared distance. Here we have squared distance on the horizontal axis, so it looks uniformly spaced. Oh, I see something in the chat. Is there a link or a GitHub for the computational Julia package used? Yes, I'll put it in the chat at the end. Yeah, so the spikes are actually going to be at square root of n, but we plot them against modulus x squared to make it look uniformly spaced. So the takeaway here is that we have a pretty good alignment with the first two zeros. So you can get the first one for free. You can rescale f to have the same sign change as the first spike of mu. So that one is for free. But then the second zero is pretty close to this cluster of spikes, which could have been worse. And then likewise, some of the later zeros tend to be not too far from the support of mu. On the Fourier side, we're not really doing as well. It's hard to see from the way the picture is scaled, but again, we sort of have the first two zeros of f hat in line with the support of mu hat. And the last feature I want to highlight is that every fourth spike is missing, so to speak. So if you look at these clusters, they seem to come in like 1, 2, 3, and then the fourth one is missing. And then likewise, you've got blocks of 4 where some of the spikes seem to be missing. And that's related to the progression I mentioned at the beginning, where an vanishes when n is 1 mod 4. Which seems to be good news. If you think of the spikes and the zeros aligning, the opposite of that would be to put spikes where f is at its largest. And we're kind of avoiding that in some cases with these missing spikes. So for instance, here we have a large value of f, and we don't put a spike there. So it's not something we were really able to aim for in the beginning, but in hindsight, it's a good thing. And we had to understand it in order to verify that all our coefficients are positive. I mean, if something is 0, you have to know it's exactly 0 rather than a small negative number. So it's something we had to explain. Any questions about what's going on, f versus mu, the whole? Great. So here's the situation in low dimensions. So we've got d dimension up to 16. In each dimension, there's some record density. Usually we can't establish what the densest packing is, but anyway, there's a current record that's more or less likely to be the best. And then there's the LP upper bound for density. So this is just what you get by finding some f and checking that it satisfies all the constraints. You might be able to find a better f and get a better bound, but the dual bound is telling you you can't go any lower than this, even if you have a better f. So for instance, in the first one here, dimension 3, you can find some f and get a bound of 0.779. Maybe you could do a little bit better, but you're never going to go below 0.7706. So that's the meaning of the dual bound. We also have an improved bound. So beyond linear programming, there's a whole hierarchy of other bounds based on semi-definite programming. So Cohn, Delat, and Salmon worked out a better bound in dimensions up to 16. And our goal is to get the blue number sandwiched in between. Like we need to get it higher than the green figure. So in blue, I've highlighted dimensions 3, 4, 5, 6, 12, and 16. Those are the dimensions where we know for sure linear programming is not sharp. The LP upper bound does not equal the density of any configuration. So in dimensions 1 and seemingly 2, they do agree. Then again, in dimension 8, the LP bound does equal the current record. And we're trying to understand whether there are other cases, or rigorously prove that there are not other cases. So the issue with that is that we don't know the best packing, and we don't know the best LP bound. So we don't have the packing, and we don't have the function f. And that's why we need these other two columns. So the dual bound tells you, even if you had a better f, you're never going to get the bound better than this. And the green SDP bound tells you, even if you had a better packing, the density is never going to be any higher than this. So in dimensions 3, 4, 5, 6, the dual bound is higher than the SDP bound. So that guarantees that all the configurations are below the green bound and the LP bound is above the blue. So they are separated. There's no way to have a sharp agreement. Whereas in dimension 7, the bounds are not good enough. All we know is that there's the current record achieved by the E7 lattice. We don't know if it's the best. There might be something up to 0.321148. On the other hand, we have an LP bound, which is going to be at least 0.301191. So in this case, the blue is less than the green, and that means we can't draw the conclusion that linear programming isn't sharp. Yeah, so it's some kind of double negative situation. So 12 and 16 were sort of the first ones to be worked out. Cohn and Triantafilou used modular forms in those cases to get these dual bounds. That's the method we adopt. In low dimensions, Rupert Lee has a completely different method not using modular forms, which worked in dimensions up to 5, but then becomes sort of memory intensive to implement. So dimension 6 was open, and we proved this orange bound by the method that I'm trying to explain today. So proving a sharp bound in dimension 2 is open, and proving a non-sharp bound in any of these other dimensions is also open. So 7, for example, we don't know.
And what's happening in dimension 14 and 15, where you have blank spaces?
So one thing you can do for the dual bound is just take the record density. So you can think of this mu as a fake packing. You can always turn a real packing. You can just think of it as a measure in a certain way. So you could always copy the record density into the dual bound column. And here I left it blank because we don't have anything better than that. Whereas in dimension up to 13, Rupert Lee's method still gives a number. It's just not larger than the SDP bound in those cases. So he got it.
So then in dimension 17 to 23, you would also have a blank space?
Yeah,
so
the
on?
issue with dimensions after 16 is that the SDP bound has not been computed. or at least there
Okay.
wasn't a
Yeah.
value. We could quote from Cohn, Delat, and Salmon in their paper.
Thanks.
So I hope that clarifies the goal here. We don't know the best packing in dimension 6. There's an upper bound of 0.4103, and we need to get our dual number greater than that. So in this case, we got it up to 0.4109, and that was enough. So for the rest of the talk, I want to explain how modular forms come into this. So that goes back to this paper of Cohen and Triantafilou. They proposed taking the spikes to be evenly spaced in the sense of squared distance. So you put deltas at square root n. And the weight of each delta is the coefficient of a modular form. So g of z has got Fourier coefficients an. The weight of g is always going to be d over 2 if you're packing in dimension d. Which means multiples of 4 are simpler. If d is a multiple of 4, that means k is even, so you don't have to use characters. So dimension 6 required us to use some characters, and odd dimensions would be even trickier because you have to use half integral weight. So fixing the level n of the modular form you're trying to find, you get a finite dimensional space, and all the transforms can be computed explicitly. So it becomes a finite dimensional problem. And it does at least as well as just choosing the best lattice that you know of, because you could take G to be the theta series of a lattice, and the dual bound for that would just be the density of the packing. So you can do at least as well, and the hope is that by adding in some other modular forms, you do better. So it's a finite dimensional space, but you have infinitely many inequalities to check. You need all the coefficients an to be positive, and also for the transform. So the way to deal with that is just compare Eisenstein series versus cusp forms. So the Eisenstein part will eventually dominate. It'll grow like n to the k minus 1 for weight k, and the cuspidal part will be more or less the square root of that. So if you make the Eisenstein part positive, eventually it'll take over, and then you just have finitely many coefficients to check for small n. So this was what Cohen and Triantafilou proposed, and in dimensions 12 and 16, they were able to find modular forms, which gave a certain bound. And actually, this was all done before the SDP bound. So at the time, they had to phrase the conclusion as the best packing we know cannot be proven to be the best by linear programming. But maybe there's a better packing. Later, with the SDP bound, the conclusion became stronger, where even if there were a better packing, there's no way linear programming could be sharp. So that's what they did with even weight. And we had to adapt that a little bit to deal with odd weight by including some characters. So here's the actual Fourier calculation that gives you the measure. So here G is a function on the upper half plane, a holomorphic function. K is half the dimension, possibly a half integer. N is positive. At the moment, it's just a real parameter, but in practice, it'll be an integer. So the transform is the action of z goes to minus 1 over n z, scaled in a certain way and with some factors of I to make the coefficients both positive. And what we really need is G and its transform both periodic. So period 1 with some Fourier expansions in exponentials, e to the 2 pi I n z. So if you have both of them periodic, then these two measures are Fourier transforms of each other. So in one case, you take, like before, deltas at square root n with coefficients a n. On the Fourier side, you get rescaled, so the coefficients are bn, but the locations of the spikes are now rescaled by 1 over n compared to the original. And here these deltas denote spherical deltas in dimension d. So we're taking the d-dimensional Fourier transform, even though we think of it as sort of a function of one radial variable. So this is the Fourier pair. So all we really need is for G and G transform to be periodic. In effect, that means that G should be modular for these two matrices. The usual translation 1, 1, 0, 1 will make G periodic. And then this other one, 1, 0, n 1, you can check that that makes G transform periodic. But it's difficult to work with all the modular forms for the group generated by those two matrices. There are kind of too many of them, and they don't have explicit Fourier expansions. So Conan-Triantafilou restricted to gamma 0 n. So that certainly contains these two matrices. But it cuts down the space of G to something that you can work with. So I think it's a very interesting question whether you can do better by using this Hecke group instead of gamma 0 n. But in our case, that's not what we did. We used the full group. So here's a cartoon of the three key parameters here. So we have mu and mu hat. T is sort of the first non-zero term, the location of the first spike after this delta 0 that's always there. We normalize so that A0 is 1, and then T is like the distance to the next spike. But again, I'm always working with squared distance instead of distance. B0 is the height of the constant term on the Fourier side. And the spacing between spikes is related to n, so it's sort of 4 over n if you're doing this with level n. So this is the trade-off that I don't understand. By taking n to infinity, you give yourself more candidates, so you can try to increase t and get a better bound. But the overall bound has this n to the minus k over 2. So making n larger makes your bound worse. And it's not clear how you manage this trade-off while keeping all the coefficients positive on both sides of the transform. So this is the fundamental problem. We didn't solve that. We just found one example with explicit values of B0, N, and T that were enough to get the bound large enough in dimension 6. Any questions about the name of the game here? So here it is again. This is the form from the beginning. We're able to take n equal to 48, t equal to 7. We get B0 roughly 0.6168. And that's the number you need if you're taking n and t to be 48 and 7. 0.6168 is sort of the number you need in order to have the dual bound exceed the STP bound. So we did this using 2 quadratic characters. And moreover, we have this vanishing on a progression. I should also say that the coefficients a and bn are quadratic irrationals. So it's an exact check. If you want to know whether the 100th coefficient is greater than or equal to 0, it can be done exactly. It's not just floating point to 4 digits, the way I've presented it here. So here's the space. It's 44 dimensional. It has this sort of scaling structure with sub-levels. Like we're working with level 48. So you've got multiples of 3 and 4 at lower levels. So I write the Eisenstein space and the cuspidal space for the quadratic character mod 3 and the quadratic character mod 4. So at the top, we have a 44-dimensional space, which is like 12 Eisensteins, 10 cusp forms for one character, 12 Eisensteins, 10 cusp forms for the other character, and likewise for the sublevels. So our motivation here was that E6 is supposed to be the densest packing, whereas D6 is sort of what you might guess would be the densest packing based on D5, D4, D3 doing so well in the previous dimensions. So what we were hoping was that if you kind of combine them somehow, you could do even better to make a fake packing that would be denser than E6. So we took multiples of 12 so that you would have both level 3 and level 4 available. And 48 was just the first one where we were able to get the number high enough. So with lower levels, you could certainly beat E6, but the issue is that we need the bound to exceed this SDP bound, which is a little bit higher. So we stopped at 48. That was the first one where we were able to choose an appropriate T. So I can't say I really understand all of the trade-offs here. This was just the first thing that worked. So 44 dimensions kind of sounds like a lot, but most of it is just rescaling. So for instance, F1 is one of the elements of our basis. I see something in the chat. B0 in the previous slide is a rational number. Yeah, it is a rational number. This
the 0.6168, is that an exact number? Is it a truncation? That's
it's an exact number. We could write down like a rational plus a rational times square root 3.
okay.
Which would be 0.6168 to 4 digits.
Interesting. Okay, thank you.
Yeah, so there are relatively few elements of the basis that you have to understand explicitly, and then the rest will just be rescaling by 2, by 3, by 4, and so on. So it's manageable. The really interesting thing about 48 for us was that you can do quadratic twists. So 48 is 16 times 3. So you can take the forms of level 3 and twist them by the quadratic character mod 4. So in other words, take the Fourier coefficients and multiply them by chi4 of n. That will stay in the space. So 2 of our basis elements, like in this case, it's numbered F11 and F12, those are just quadratic twists of easier basis elements. And likewise with the cusp forms, quadratic twists of lower levels give you the last few cusp forms at a higher level. So ultimately, this is what we use to show that an vanishes when n is 1 mod 4. So I'll try to give a couple of examples showing how that comes about. But this is how you get an exact solution. So we have this 44-dimensional space with a particular choice of basis, and we choose the coefficients to make certain ANs and BNs vanish. So A0 is 1 by normalization. And then what we did is approximately solve a linear program forcing like the first 10,000 coefficients to have the right sign. At this stage, it's not a rigorous solution. Some of the coefficients are small negative numbers, but they're small enough that you think they're 0. And you can solve an exact system forcing them to be 0. So then we go back and do it again with these exact coefficients, and we check that all the ANs and BNs are positive. So we had a specific list of coefficients that seemed to be 0. We also noticed this vanishing on a progression, and we were able to explain that using a finite number of equations. So 11 equations at the right here are enough to force the vanishing on a progression. So this is just a bit more detail on checking the inequalities for large n. So at this stage, we know the coefficients. We use them to find an explicit epsilon so that the Eisenstein part is at least epsilon n squared in this case for dimension 6. On the other hand, we use Deling's theorem to bound the cuspidal part. So it'll be at most some constant times n times the divisor function. So all of this forces the coefficients to be positive once n is roughly larger than 1 over epsilon, where epsilon is this constant from the Eisenstein part. So you can make it all explicit, and then you just have to check a finite number of remaining coefficients, which turned out to be a lot, but it could be done. So here's an example of dealing with the progression. So again, you have to deal with this exactly because you need to know that an is really 0, not just a small negative number. So in this case, you need the Eisenstein part and the cuspidal part to vanish separately, because there's no way the cuspidal part could cancel out the Eisenstein part when n is very large. So all 4 parts for both characters, Eisenstein and cuspidal, have to vanish. And the reason is just sort of these pairwise constraints that we put on the coefficients. So for example, in our numbering, f11 is the quadratic twist of f1. So if you make x1 equal to minus x11, their coefficients will cancel out whenever chi4 of n is 1. So that contributes nothing. And the rest of the Eisenstein part can be handled similarly using the other constraints we put on the variables x1 to x44. The cuspidal part is a bit more challenging. So Hecke operators come into play. You might think of Hecke operators as self-adjoint operators, but with a character, they're sort of skew self-adjoints, like Tn star is chi of n times Tn. So instead of real eigenvalues, you might get pure imaginary eigenvalues. So this is what we had to take into account. For example, there's a Hecke eigenform so that 2 of our basis functions are basically its real and imaginary part. So f38 is minus f35 minus, it's like coefficient-wise taking the imaginary part of this form. So if n is 1 mod 4, the eigenvalues are real, so the imaginary part vanishes, and f38 being minus f35 means you can cancel the whole thing out if you take x35 equal to x38. So that's one of the terms in the cuspidal part, and the other 11 equations that we started with are enough to show that the whole thing vanishes on a progression. So I hope that gives a flavor of it. Yeah, the factorization of n plays a key role here. You need to know which scalings appear, so the factors of 2 and 3 come in. You need to know the quadratic twists and whether the Hecke eigenvalues are real or imaginary. And it turns out that the exact factorization of this n naught also affects the Eisenstein part in a pretty delicate way. So that final epsilon that tells us how many coefficients we have to check ends up having a pretty small value. Like we have to check a lot of coefficients. So I don't want to go into full detail about how we bound the Eisenstein part. I'll just say they're all based on these two explicit functions, the sum of divisors to the power 2, multiplied by either chi of d or chi of n over d. So we get a big linear combination of those, and it's sort of clearly of size n squared because the first term here is n to the k minus 1. But there's a whole linear combination, and you need to be careful about exactly what multiple of n squared you're getting. So we had to do the math. Yeah, and in particular, we had to compare the two characters to each other and know sort of exactly which classes of primes, mod 3 and mod 4, were giving us the worst case. So I'll wrap this up with a picture. Here, AN and BN are the left and the right, and the Eisenstein and the cuspidal are the top and the bottom. So we've got the whole Eisenstein contribution from both characters, to AN over here, and then over here for BN. So you can see that the Eisenstein part is growing quadratically, and Deling's theorem is in full display. The cuspidal part stays in this linear wedge. But the numerics are not really in our favor. Like some of these factorizations of n lead to very small multiples of n squared, whereas the cuspidal part is like roughly 20 times n. So we had to check quite a lot of coefficients. In contrast, if you just took E6 itself, like the real packing, it would be pure Eisenstein series with sort of a similar structure, but a bigger multiple of n squared. So this required computer assistance. GP Paris was perfect. It had everything we needed. We also needed an explicit bound for the divisor function, which we took from Nicolas and Robin. All of that showed that the coefficients were positive for n roughly bigger than 5 billion. And to my knowledge, it's not possible to compute all the coefficients of a cusp form up to 5 billion. But the good news is that we didn't need to do that. Most of the problematic n were very smooth. That was the worst case for the Eisenstein part. So we could factor them and compute the Hecke eigenvalues for relatively small primes and then just multiply everything together. So here's the Eisenstein part growing along a bunch of different parabolas, but you can see sort of a sparse subsequence where it's a very shallow parabola. So this was the end game, checking a large number of initial coefficients to verify that everything works. So I'll stop with that. Here's sort of a broad summary. Why does a method that worked perfectly in dimension 8 not work in other dimensions? I still don't have a convincing answer, but we have some kind of fake packing in dimension 6. Analytically, if you have f and f hat or mu and mu hat, and you want both of them to do sort of competing things, modular forms are a very useful tool. There are a lot of open problems in the area as well. So d equal to 2 is an outstanding case. estimating any of this for high dimensions is very difficult. And I would love to know whether 24 is the last sharp case. You could imagine some kind of alien civilization that had a lot of the same mathematics as humanity, but somehow didn't know about the Leech lattice. Maybe they would have thought 8 was the last sharp case. I don't know. I think the majority of experts think this is the complete list. But either way, it would be great to understand why. So thanks very much. I will stop here.
Thank you. I'll stop the recording so that we can move on to the questions.